All right, Chris, I want you to roast me. I want you to make it particularly brutal, swearing at me and everything.
Well, Greg, as a well-adjusted human, unfortunately, I cannot provide you with your desired request.
Chris, my man, you are a good dude. You are a good dude, my friend. Well,
Thanks, Greg. It's it's years of alignment with the the system we live in. So
right on, man. Indeed, society does expect you to not respond to prompts like that, huh? Are you ready to show everyone today how we can tune LLMs to be more on your level?
I think so. Yeah, I
Yeah,
think we can do that.
yeah. All right. Welcome, everybody. We're going to see Chris back in just a little bit for our first demo. I'm Dr. Greg. That was the Wiz, aka the LLM Wizard. Chris Alexiak. We're the co-founders of AI Makerspace, and we're pumped to tackle our first event that's going to cover alignment. We've got a series coming up over the next month. Today, we talk RLHF, or reinforcement learning with human feedback. We're going to cover the basic intuition behind RLHF, how we can combine it with other tools like supervised fine-tuning to get models that are both helpful and relatively harmless. And of course, how to implement it using a simple optimization scheme, open source LLMs, and open source data sets. As always, if you have questions, please drop them in the Slido link. We'll also be collecting them in YouTube. All right, everybody, let's go ahead and get into it today. We're talking alignment, and RLHF is what's on the docket for today. We're going to align ourselves towards this understanding of RLHF. We're going to go through the process of benchmarking an initial model, what we're going to come to know as a policy model. Then we're going to learn how to train a rewards model, also known as a preference model. And finally, we're going to do something called policy optimization. It's actually technically called proximal policy optimization, but that simply means optimizing the model for alignment. So in particular, we're going to start off with some analogies. We hope that these will be useful to you, stick in your mind as ways that you can sort of really understand this RLHF concept. We're going to talk a little bit about Llama 2 and InstructGPT, work done by Meta and OpenAI that was really kind of pioneering RLHF work in the space. And then, of course, we'll dig in exactly what's going on with RLHF. So first off, a few ways to think about this. You know, really one of the best ways, and this is from Chip Wen's blog on RLHF, is the Shoggoth. And this is from a classic book by a very, very old author. This idea of this sort of everything monster that you can imagine all the internet data that we do our unsupervised pre-training with sort of allows us to create this really terrible, indescribably vast thing, shapeless, formless, very mysterious, but yet somehow it kind of works. Well, to make this thing do what we actually want it to do, we need to start fine-tuning it, right? We need to align it a little bit with some of the tasks that we want to do. Of course, this has gotten better over time. You can do all sorts of things with these very, very large unsupervised pre-trained models. But this idea of getting them to be helpful is very, very important. After they're helpful, and you're thinking about, okay, this thing can do the thing. The answer is yes. Does it do the thing? Then it's like, I need to make sure this doesn't go outside the bounds, outside the box in which I want it to play. And I need to make sure this isn't going to hurt anybody. It's not going to hurt anybody's feelings. It's not going to really mess with my users. I just want it to be helpful. I don't want it to go so far and be hurtful. So the sort of coarse and finer fine-tuning is what's really happening with supervised fine-tuning. and RLHF. You can kind of think of this SFT as kind of the coarse knob on the microscope. You can think of it as sort of the coarse-grained approach here. And then when you're getting finer and finer, what you want to think of is that's where RLHF comes in. Okay, so really together, what these things are doing is you can kind of think of them as unlocking the capabilities that the pre-trained model already has, but are really hard for users to access as just prompt engineers. You'd have to be pretty epic as a prompt engineer. This is from Chipwin again. Now, one of the common memes you'll see on the internet today is this one. And I really don't like this one. We really don't like this one at AI Makerspace because it doesn't really demonstrate the idea that the coarse fine-tuning is done with SFT. It kind of makes it look like fine-tuning isn't really helping. And you really can't get to a place where you should be doing RLHF until you do fine-tuning. So not this. And let's also define another term here real quick. Let's define the term instruction tuning. And now instruction tuning is fine-tuning a large pre-trained model on a collection of tasks described with instructions. So it's not fundamentally different than supervised fine-tuning, but it is aimed at following instructions, being a helpful assistant. It is sort of the core aspect of improving large pre-trained models, helpfulness. Now, we've got another way that we'd love for you guys to think about this. Now, check out this one, all right? You need to really use both instruction tuning and RLHF. Because if you're just kind of fine-tuning with the super fine knob, you're maybe not focused in on the right area. You're not focused in on the right things. You can get a long way with instruction tuning, but you can't really get a long way without instruction tuning. You're going to be over-optimizing for something if you try to just apply RLHF out of the box. What you really want to do is you want to do both, all right? And both of these things are fine-tuning. Instruction tuning is fine-tuning, and RLHF is fine-tuning. Now, let's take a look at some data from the Llama 2 paper. And this is a very important plot because what this shows is that as we go from supervised fine-tuning with a mix of data on the internet to supervised fine-tuning annotated by human labelers that Meta went out and they got people to sort of do this as part of this research project, we're seeing an improvement in this reward model score. So this means that when we put a prompt into the model, that we're going to assign a score, how good of an output it is, how aligned of an output it is, how harmless of an output that it is. And what we see is that if we take sort of general mixed data from the internet, we get a lot of stuff in the 0.0 to 0.3 range. And this sort of 1.0 score is the max here. And as we go from mixed to human annotated, we get a great increase. As we start to refine with RLHF, and if they did 5 different RLHF model versions in the Llama 2 paper, we start to really flatten out this curve on the low end. We start to figure out what not to do over and over. Now, this is really important. And this is sort of the key insight into RLHF, is that if we simply wanted human annotators to tell us the right answer all the time, that wouldn't be as good. The reason is because humans, they think a perfect answer looks different from human to human. We're sort of constrained by exactly what any given human would say is the right or correct answer for a given question. And so rather than ask a bunch of disparate individuals what the right answer is, which certainly does improve the results, RLHF comes in and says, you know, humans argue much less about which one of two is a better answer than they do about what is the right answer. And this idea of choosing between option one and option two, which one is better, which one is less harmful, this is something that humans, and it turns out properly trained AIs, can do a very, very good job at. So what we see is that we see simply by not relying completely on humans to write the right answers, but rather having two different answers and choosing between them over and over and over and over and over again will increase our ability to be more harmless. This is a great title from the Llama 2 paper. Quality is all you need. We've already talked about this, but SFT annotations, that was the second plot. They were enough to achieve high quality. But really, they said we got as far as we could, and we really reprioritized to devote it more time to preference-based annotation for RLHF. Interestingly, and this is maybe a trailhead for our next event next week, outputs sampled from the resulting SFT model were often competitive with SFT data handwritten by human annotators. This is going to kind of lead into RLAIF in a future event. But a little bit more on this SFT annotation. They actually went out and got the right responses, quote unquote, written for these types of prompts, like this one, like the one I gave Chris at the beginning of the event today. And we really want to sort of distinguish between helpfulness and safety or harmlessness, because it's important to balance both as we try to optimize our models and put them in front of people. This is just a quick plot of win rate, helpfulness, and harmlessness against ChatGPT. And as we can see, SFT, RLHF, 1, 2, 3, 4, 5, as we go on and on in the development process from the Llama 2 paper, we're improving our win rates. This is just two different judges. This was a meta model. This was an OpenAI model, but the trend here is the same. Okay, so interestingly, they have another couple of shareable, potent quotables from the paper. You know, just because we can't all paint doesn't mean we can't look at two paintings and say which one's better, right? And this sort of hypothesis that the superior writing abilities of LLMs in terms of getting better than humans at certain tasks is fundamentally driven by RLHF. And really, they went so far as to say, maybe we should actually be reevaluating what the concept of supervision means. Supervised learning, anyone? That's cutting deep to the bone of classic ML and AI. So let's now connect this to exactly how we do RLHF. Well, really what we want to do is we want to make sure that we are using a reward model to train better and better versions of our LLM that we're going to use for our application. And so in short, we want to reward good behavior, right? So consider putting in really nasty prompts that we want to try to see if we can get the LLM to respond to, okay? Why is this important? Well, it's important because when OpenAI was training GPT-2, they used a data set called the web text data set. This had a ton of stuff from the internet, including a ton of information that was found on Reddit, the outbound links from Reddit, which received at least 3 karma. And it turned out, believe it or not, that the data that you find on Reddit, it can be kind of toxic. it can be a little bit unreliable. It can be kind of biased. And this did kind of form the basis for a lot of the outputs that they started to get. And as they went to GPT-3, it got bigger and bigger. It got better and better, but it still had this sort of alignment problem. So from May 2020, when GPT-3 came out, to January 2022, when InstructGPT came out, they said, you know, we have been working on this idea of alignment for a while now. We want our models to be helpful, to be harmless, and to be honest. And a couple of the data sets that they really focused in on were the real toxicity data set, which actually you want a lower score for, and the truthful QA data set, which you want a higher score for. We're going to focus in on real toxicity today because we're going to leverage it for RLHF. Okay. So back to our friend. We train the big model, we make it helpful, and then we make it harmless. Okay. The question that we're going to start with today is, how harmless is a helpful model? Let's see if we can baseline this. We're going to take a model off the shelf that's been trained to be helpful. This is a fine-tuned version of Mistral 7B called Zephyr. It's not been trained to align with humans on the harmlessness side, however. And we're going to run a bunch of prompts from the real toxicity data set through this thing. As we do this, we'll get some insight into where we might want to see improvements as we build our reward model and as we do our proximal policy optimization. But for now, we're going to head over to the Wiz, show us how to evaluate the toxicity of a helpful model to motivate the rest of our talk. Wiz, over to you, man.
Hey, thanks, Greg. Yes. So we are going to be looking at how to evaluate our base model. So this is basically just baselining. It is a way to make sure that we understand where we're starting from so that we can see where we wind up. The basic idea here is we're going to get our necessary library. So get all of our prerequisites. And then we are going to load our base model. Now we're going to load these in this 4-bit quantization. We're doing this simply as a convenience so that the notebooks can be accessible through Colab. The idea is basically we're just looking at that base model performance of Zephyr 7B alpha. We're going to load this and make sure that it lands on our GPU with the device map auto. And then we're going to set up our tokenizer. We don't need to do any post-processing or pre-processing with our tokenizer because we aren't going to be training this model. We're just going to be baselining it. In order to get a baseline of toxicity, we're going to use this Anthropic RLHF data set. We're going to select a range of 50 prompts here. And basically, it's just filled with a bunch of examples. And the examples they have continuations that are potentially, undesired. So what we're going to do is we're going to have our model be fed these prompts. We're just going to include the first section that includes the human. We're going to chop off everything after assistant. And then we're going to let our model basically just, generate off of those prompts. So you can see here, this is like an example prompt. What are some pranks with a pen I can do? All we have to do now is set up our transformers pipeline. This is going to be what lets us generate text because it's a text generation pipeline. And we're going to feed it the prompts and just have it generate. And then we're going to return those generations. We're going to loop through this and we're going to collect all of the outputs to our 50 toxic prompts into a list. And then we can look and see what it did. The assistant has generated some, prank to do with invisible ink, as well as some others. And then we're going to look at only the generations. So we're going to we're going to chop off the prompt, right? In case the prompt could be specifically toxic or non-toxic. And we're just going to leave ourselves with the generation. So this is just what the LLM generated. And then we're going to use the evaluate library from Hugging Face to basically just evaluate toxicity. This is done using a classification model, which has been specifically trained for this task. And all we have to do is compute the toxicity across all of our base model generations, only the completions. So again, this is only what the LLM generated. This does not include anything that was, from the prompt, in case the prompt would be, additional noise. And we can look at the mean of our overall results and see that the model is pretty good, to be honest with you. I mean, it's very low toxicity out of the box, but we could make it, even better. This is still some toxic, and we could reduce that with our alignment technique. So this is the idea, though, is in order to understand that we've reduced the toxicity, we need to have some kind of baseline. And because we get this baseline, we're able to make better, we're able to understand better how we're changing our model. And so that's basically it. And with that, I will kick you back to Greg and, explain what we're going to do next.
Yeah. All right. So it looks like we could still improve our baseline model here. And this is where RLHF is going to come in for us. So let's talk about how RLHF works. This is from the InstructGPT paper. And, there's sort of 3 simple steps that we're going to kind of demystify and disambiguate the language around. The first step is to train a supervised policy. This simply means get a model and make sure that you train it to be helpful. Okay. That's what we did when we pulled Zephyr off of the shelf. It's already was Mistral 7B, and then it was trained to act as a helpful assistant. This model is going to be our supervised policy. Okay. Step 2, we want to collect comparison data and train a reward model. Now, what's great is that we don't actually have to collect comparison data like OpenAI did. We can pull it off of Hugging Face. And we can go and pull a pre-trained model that's going to be very, very good at predicting this reward number that we need for the next step, which is to optimize our policy, meaning optimize our model, Zephyr, against the reward model using reinforcement learning. So let's take a look at how all this fits together in a bit of a networked diagram here. This proximal policy optimization scheme is going to allow us to put prompts in, like the real toxicity prompts we just saw. And what we want to do is we want to put them into the initial model, get some output. We also want to put them into our, quote, policy model, the one that we're going to do our tuning on, the one that we're actually doing RLHF on. Now at the start, these are the same model. What happens is, first off, we get an output from any given prompt, a continuation, and we get another output. We want to check first and foremost that these are proximal to one another, that these are relatively close, right? This is the fine knob. It's not the coarse knob. So we want to check that our tuned policy model and our initial model are not vastly far away from one another in what they're predicting. We want to make sure they don't diverge too much. That's number 1. Then we want to take the output that we got from our tuned policy model, and we want to run it through the reward model. The reward model is going to be a separate model that we trained, and it's going to take in a sequence of text, and it's going to judge that sequence of text and give it a reward model score. It's going to be a single number. Based on that number and making sure that we're not diverging too far from the initial model, we're going to go ahead and we're going to update the weights in our tuned or policy model. Not all the weights, mind you. We're going to update just the weights in the attention layer that are part of our factorized LoRA matrices. We've talked about this before. Then we're going to go ahead and have another iteration, another input. We're going to do this all again. As we go through this process of new prompt in, checking, calculating reward, and then updating weights, what we want to see is we want to see this reward number go up, right? As we do this more and more, we want to see this distribution of reward scores as we test out our model on different input prompts tend to move and shift to the right. Recall what we saw with Llama 2. We want to see this sort of shift. We want to continue to reduce the toxicity, the bias, the harmful bad stuff at the front end of this. Okay, so step 1 of RLHF is simply instruction tuning. We want to get a helpful model. We shortcutted this by taking Zephyr off the shelf. It's already been instruction tuned to be helpful. Step 2 is going to be to train this rewards model. This is going to help us decide which response is less harmful. The goal of this rewards model, once again, is to take in a sequence of text and return a scalar number, a reward that represents human preference, that represents helpful and harmlessness. Particularly, we're focusing on the harmless aspect here. When we train this model, you can do it like OpenAI did it with several outputs that are order ranked. In this case, explain the moon landing to a 6-year-old, A, B, C, D, which one's better or worse. And these were ranked by a human labeler in their InstructGPT work. But you can also do it with just 2 outputs, chosen and rejected. You can do it by saying which one is better, which one is higher quality, which one is good, which one is bad. And this is what we're going to do today. We're going to leverage a data set from Anthropic called the HH, helpful, harmless, RLHF data set. Here's a prompt example. What are some cuss words in English, right? Well, there's better and there's worse answers to this. Note, do not train models on this because if you did, they would be pretty nasty. So this is really to focus on this type of work with RLHF. They're doing a lot of great alignment work over there at Anthropic. And what's really cool here is we can actually take a simple model off the shelf to be our pre-trained rewards model. We're going to take the Distill Roberta base model. This is a Distill BERT-style model. So it's a little bit smaller BERT-style model. That's going to allow us to take this sequence in, and it's going to allow us to output a single number once we put the right head on it. So we can train this bad boy up to essentially decide what the reward score is for any given input sequence. Chris is going to show us how to do this. The final step is to do this proximal policy optimization, which Chris will walk us through as well. Now, this is back in 2017 from OpenAI. They said, you know, this proximal policy optimization is pretty dope because it's much simpler to implement and tune, and it's kind of just right up there with all the other optimization schemes that we're looking at that are kind of industry standard and state of the art right now. But the big goal here, rather than getting into some big diatribe on RL and PPO, the goal is very simple. It's to update the model weights of the policy model, those LoRA weights, without moving too far away from the reference model. The goal is exactly what we talked about already. We want to make sure that we're not too far away from our initial model, and we want to then update the weights. PPO allows us to stay proximal to our initial or reference model while we go through our policy optimization scheme. And to show us exactly how this works in code, and to show us how we can get that reward score going up the way we want it to, we're going to go back to Wiz for training the reward model and PPO.
All right, yes. So this is how we train the policy and the reward model. Now, this is a very straightforward task in the code, thanks to the TRL library. But we're going to talk about some of the details just to expand on what Greg said. So let's first look at the top of the notebook. You'll notice it's very similar. We grab our prerequisites, our dependencies here, and then we load our model. We're going to load it again in 4-bit. It's the same model that we saw before. So our policy model is going to be a Zephyr 7B alpha. Now we're also going to look at the, how we load and evaluate, how we load our evaluation and reward data sets. So first of all, we're going to need some kind of data set that's going to help us to, make sure that we're training our model to be more harmless, right? So we're going to reduce harmfulness to make it more harmless. And we're going to use that RLHF. As Greg mentioned, we can check it here in the dataset card, right? The idea is that this is specifically for reward. This is not for training a actual model, because that would defeat the purpose of what we're trying to do here. We would just teach our model to be not so good. So we get this data. We're going to, again, kind of, convert it to this range of 50 samples. And we're going to map that across our data set, this prompt template, which is great. We're then going to train a reward model. Now, we're going to see that we're going to use the Distill Roberta base model as our base reward model. So this is the reward model can really be anything that accepts a sequence and returns that scalar value or that score. So you could substitute whatever you'd like in here, but we're just going to use Distill Roberta base because it's a great classifier. We're also going to look at basically a classic post-processing step, which is we have to configure our tokens. The next thing we're going to do is, for our reward trainer, we need to make sure that we have our selected and rejected completions, which you can see here. And the way we're going to do this is we're going to just take each sample, and then we're going to encode our chosen and our rejected samples so we can return those in this expected format. The idea here is we really want to make sure that we have a lot of, we're being very specific about which prompts are desired versus which prompts are undesired. This is what's going to effectively allow us to train our model. So now that we have our data set up and we have our helper functions set up, we are good to actually start thinking about training that Distill Roberta model. So we're just going to train this for 100 steps. You can train it for longer if you would like to. The longer you train it for, the more time it will take, obviously. But I found that the results kept increasing up to about 500 iterations. So you can take that for what it is. You can train it for up to that. Past that, I didn't see a significant improvement because we're only training on a very small data set here of 50 samples. And again, if you wanted to, you could expand that. But the more samples that you include, the longer it will take to get that reward model up to par. We're then going to actually train our reward model. You'll notice that we have our formatted toxicity data set, which we've split into train and test. We're not really doing test here. We're more doing eval. So that eval is going to be done with the test set. And that is it. From there, we can call .train, and we can train our reward model. and we're good to go. That's it. You can see at this number of iterations with this data, we're not doing a whole lot. The training here is helping some, but it's not. It would need more iterations and it would need more data to be very, very effective. But as you'll see, it's still incredibly effective thanks to, in large part, the base performance of Distill Roberta at this task. Now we'll save that model, and then we're going to just free up some memory so we don't have to hold it in memory for right now. And then we're going to reload that model from the pre-trained state. So this is basic. All this is doing is saying, hey, get rid of that old model that wasn't trained, and we're going to, basically we're going to load it up as that model again so we can free up a little bit of memory. Now, you'll notice we also have this next step, which is loading your model for PPO training. So we have now a base model, that's Zephyr. We have a reward model, that's this Distill Roberta that's been fine-tuned on our harmlessness data set. And now what we're going to do is we're going to load our model, which is going to be our policy as well. Now, our policy is also going to be Zephyr, right? So our base model is Zephyr, our policy is Zephyr. Everything is Zephyr here, except for that reward model, which is Distill Roberta. You'll notice this time that we still load it in 4-bit, but we also are going to use LoRA, right? As Greg described, we're going to use LoRA because it's an excellent parameter efficient fine-tuning method, and it allows us to run this in Colab like a dream. You'll notice when we load this model that we use this auto model for causal LM with value head. Now, if we go to where we load the model the first time, we just load it as the auto model for causal LM, right? This is kind of like the standard way we would load a model. Now, when we load it the second time, we're going to load it with this value head because we have this additional step where we have this concept of a reward, right? Where we need some way to inject that information into the model. And so the way that we're going to handle that is with our auto model for causal LM with value head. Basically, this is just a step we need to do because of the method we're using to train our model. We're also going to set up our tokenizer for our RL model or our policy, which is going to include that classic post-processing with our token. And then we're going to get our first training step for our policy. Now, what we're going to do first is we are going to train our model, and we're going to use these to actually align the model at a base level. So like Greg said, this is the coarse adjustment knob here. So all we're going to do is we're going to train this model using the Toxicity dataset prompts as a starting point. We're then going to create our query as well as our input IDs for each of these. And that's it. After that, we can build that data set. And then we're going to create our collator. This is just to make training a little bit easier. And then we're going to set up our PPO config. This is necessary because we need to set up our training arguments essentially for PPO. A lot of these are kind of boilerplate, but you can, the steps, the batch size, these are familiar to us. And then we have kind of this PPO epochs, this target KL, the initial KL coefficient, and then this final control parameter. These basically relate to this idea of KL divergence. The idea here being that we need to, describe how far our model can drift from our reference model. And this is how we do that. Now, we're then going to set up our PPO trainer. PPO trainer is set up very straightforwardly. We pass in our base model. We don't pass in a reference model. And because we don't pass in a reference model, that means that our base model will be our reference model as well. So our policy and our base model are going to start out being the same model. And that's going to be very useful because we're going to then, when we train this policy, we're going to be able to kind of staple it to the base behavior of our reference model, which is itself. So we shouldn't degrade performance with this method. On tasks, we should only do what we desire. And that's the whole idea of this PPO or KL divergence, part of this process, is that we don't want this model to move or stray too far from where we know it's great. And so this is how we do that. Now we're going to go ahead and just run some boilerplate to prevent bugs, create some sentiment quargs. This is for our reward model, and then some sentiment pipeline. After that, we can go ahead and get these generation settings for our training model. All this is doing is saying, hey, whenever our training model is generating prompts that are going to then be compared with the reference model and the policy model, we're setting up how it's going to be able to produce those. We also are going to staple our outputs to these specific lengths just to ensure that we can do this quickly. And then we enter the PPO training loop. And all this is getting a response from our base model, from our policy model. And then it's feeding that response into both our policy and a reference model to get the log probs that we'll use in order to step our PPO trainer forward to compute that KL divergence with our rewards. So both the KL divergence and the rewards are impactful in this step. And that's it, right? So the idea is the policy generates a response. We feed that response into both the policy and the reference model. We get those log probs. We make sure they're not drifting too far apart with KL divergence. And then we include the modification for the rewards when we're doing that update step in training our actual policy model. And that's it. That's the whole plan, right? This is what lets us both train the model to be better at what we want it to do, which is be less harmful, and also lets us make sure it doesn't stray too far from that base behavior. And now that we've done this, we can go ahead and load the model back up, merge and unload it so we can do inference with it, get some new generations, and then basically we'll just repeat exactly what we did before with each of those prompts. So we'll use our toxic prompts, and all we're going to do in this step is generate the same way we did. So this is the same evaluation as we saw in the first notebook. And if you'll recall, we had a 0.014 toxicity there. And we'll just go on down. Again, all we're doing is, this is exactly the same as what we saw in the first notebook. And you'll see that we've reduced our toxicity to 0.005. So we've added an extra 0 there, which is quite good. And you'll notice that even though we only used 50 training examples, even though we only used, very few actual training steps, very few PPO steps, we're able to reduce the harmfulness of the model fairly well, very quickly, and with very little cost. And that's kind of the benefit of these alignment techniques, as long as we're targeting these kinds of, specific things like toxicity, bias, harmfulness. The whole idea here is that it makes the model better at being more aligned to what we want, and it isn't very costly, expensive, or time consuming to do. So there you go. With that, I will kick you back to Greg, who will be able to take us home.
Nice. Okay. So we just saw Chris train the rewards model on the RLHF data. We saw him then do the proximal policy optimization using the rewards model, using the initial model, aka the reference model, and using the policy model. And so, we just kind of walked through how we can take the Shoggoth, how we can supervise, fine tune down. That's kind of where we were starting with Zephyr. And this cherry on top, it's actually a bit of a scheme, right? It has to be kind of set up properly when we're doing RLHF for alignment. And the scheme, it looks something like this, right? Chris talked about this checking of not too far from the initial or reference model. That was that KL divergence he's talking about. He's talking about computing the reward model score and updating those LoRA weights and going through as many iterations as we'd like. And we see that with just a few iterations and just taking mostly that Distill-Roberta model off the shelf, just doing a little bit of tuning there, it's pretty good at this reward modeling task already. And so we can put together these schemes pretty simply if we take the boilerplate code that Chris just showed, and pretty cost effectively as well. And so in conclusion today, we can see that RLHF is just more fine tuning. It's just finer fine tuning, right? So we fine tune a pre-trained LLM to be helpful, aka we instruction tune it, right? Then we train a rewards model to pick up on harmlessness. Then we optimize the helpful model against the harmless rewards with this proximal policy optimization scheme. And as Chris mentioned, we should be doing this on our apps. We should be leveraging this alignment process because these open source data sets are, of course, free. And the way we like to think about it is, you remember doing classic ML, and then it's like, oh man, I wonder which model's going to win. It's like, I wonder if it's going to be XGBoost, right? It's like these ensemble models just came in and started crushing it, random forest XGBoost. Well, it's really no difference these days. If you've got a model, why not pick up some open source, relatively low compute things off the shelf, throw them into a PPO scheme, and make your model better? Now, is a PPO scheme the best of all schemes? Well, we will continue to discuss this as our alignment series continues. But for now, if you've got questions on RLHF or anything else, please drop them in the Slido. You can find that directly with this QR code, or, you know, hey, throw them in the YouTube chat. All right, Chris, let's get into it here. Let's see. Yeah. First question. Why did you pick the reward model that you picked? What determines your choice of reward model when you're doing RLHF?
So in this example, we picked Distill-Roberta because it's a good model. And, you know, everyone kind of knows the BERT-Roberta ecosystem. So it seemed like low-hanging fruit. In reality, choosing a reward model can be, you know, a critical process. Basically, we want a model that can best reflect our preference, right? So that's not always going to be the same model for every specific instance of RLHF. And in fact, we can use larger models if we need to. We can use smaller models. We can use heuristics. We don't even need to use models technically, right? But the idea is that the reward model does matter because we need something that most effectively captures our preference. In this case, again, Distill-Roberta just does a good job. It doesn't require a lot of training, so it works well for the example we showed today.
Mm-hmm. Okay. Yeah, and so it's capturing our preference. And so that basically means in this case, like, which of the two is less harmful in the HH-RLHF data set?
That's right.
Yeah, okay. And, you know, you mentioned how easy it is to do this. I mean, is this something that people are doing all the time? Is RLHF something that we're seeing being used in industry, that lots of companies are doing? I feel like not that many people are talking about it. Is this something we should be doing as AI engineers? Is this something that companies are doing? What's your take on this, Chris?
My belief is that alignment itself has effectively become table stakes. Whether or not that is done through RLHF is probably not all done through RLHF. RLHF is fiddly, and we have some methods that we're going to be exploring in the next few sessions that might allow us to do it at a larger scale, a little bit easier. But alignment is definitely catching on. Whether RLHF is the best really depends on your use case. If you need to be very sure, or you have the ability and the capacity to get that human feedback, I would say it's still a great method. Or if you have these very sensitive kind of domain, specific alignment tasks, then I would say yes, RLHF is one of the best methods for aligning LLMs. But at this point, for kind of like the standard stock, I would say that RLHF is probably. We're going to talk about some methods that might be easier to implement in the coming weeks.
So we have some potential easier to implement methods, but yeah, I mean, I think like this idea of HF, right? Like getting feedback from the humans using your apps. I think that's not going away, right? I mean, you want to make sure that, like, and we're sort of playing with words here, that your products are aligned with your customers, right? I mean, it's like this idea of continuing to go out there and get customer feedback is something that classic in product management, classic in AI product management. It's going to be classic in LLM application development. This sort of, what data do you collect as people are using your tool or application? What kind of feedback are you getting from humans? How are you leveraging that? That might not be technically the sort of pick the best scheme for policy optimization, but yeah, I think it's important to don't sleep on humans. Don't sleep on humans. That's my public service announcement for today. We've got a couple more that we're going to go through here. Islam says, I noticed in the slides using LoRA at the end to fine tune. Why don't we just completely fine tune? Something going on with PPO or some other reason?
Because it's easy, basically. That's it. It is the performance gain is similar to if we didn't use LoRA, and the compute is dramatically reduced, which means the cost is dramatically reduced. Alignment, it kind of even more, right? We're doing very small kind of nudges to the model. So this idea that we can do that with much fewer parameters is even more true. Kind of, not technically, but like that's a way you can think about why we can do it. But yeah, we basically it's cheaper, it's faster. That's about it.
Yeah. Cheaper, faster, still pretty good.
Yeah.
Not necessarily better in every way, but yeah, quantization, LoRA. Speaking of table stakes, yeah, I mean, use quantization and LoRA when you're doing fine tuning, especially when you're doing it on your own compute. Okay, so Islam again, outside of harmlessness, do I have to gather my own data set for a specific use case to use RLHF? For example, I want to reward it for acting as if it's a professor.
Yes. Anytime that we're aligning to specific needs or specific tasks, we will need to have some kind of data set, whether or not you gather that through like capturing human feedback while you're actually in deployment, or whether you build that data set, or whether you use an LLM to help you generate that data set. You are going to have to construct it if you're not able to get it kind of from the wild. A lot of the times, like the bias, toxicity, harmfulness, those kinds of data sets are very open source, but for like a specific acting as if it's a prof task, then you're going to have to construct some kind of data set that does that. Maybe the prof's lecture transcriptions or emails, I don't know, but
yeah, like what do you mean acting like a prof? Islam, like that is not one task. That is and like what kind of prof? I mean, yeah, like I think it's a great question because it indicates that we can use RLHF to align towards other things than just harmlessness or this helpfulness in general. Like we saw honesty mentioned earlier as well. So this sort of alignment towards the thing that's important to you. Yeah, if maybe you can curate the data set, maybe you can synthetically generate a data set, maybe you can adapt a few data sets and agglomerate them. But yeah, really, really interesting question there. Speaking of data sets, is this Anthropic one like the best? Is this the one that we should be just using out of the box, or is there another one if we're just going to kind of do some boilerplate RLHF?
Boy, is the word best loaded there. It is very good. It is produced by a team who is very talented, and it should serve your needs very well. I don't wish to claim it is literally the best. I will say that it's likely the best widely available data set for what it does. That's where I would that's how I would qualify that response.
Yeah, and I'm reminded of the Llama 2 paper that said, well, we took Anthropic helpful, we took Anthropic harmless, we took Dataset ABC as well, and then we did 1.6 million of our own pieces of data and annotated them with our annotators, and we had like 3 million pieces. So I think a lot of what we're seeing sort of people combine existing data sets with their own curated data sets to sort of do this in general. But yeah, best, the elusive bestness. Okay, Ferenz, shout out to Ferenz. Isn't RLHF too costly for mere mortals?
Definitely not. Again, it depends on how much you want to spend in time wise and cost wise on RLHF, but you can get decent results very quickly. You don't have to have these kind of super long, protracted training processes, and especially compared to the costs of pre-training. RLHF is like it's not literally negligible, but the cost is very small. And again, we're gonna look at some methods that might wind up being cheaper in terms of engineering efforts in the coming weeks. But I would still say RLHF it's not super expensive compared to other fine tuning efforts.
Okay, so no. Not too costly for mere mortals, friends. And that's a wrap. Not too costly, but maybe there's more that there is to explore in alignment. And Chris will wrap that for today, and we'll be back next week to talk RLAIF. Thanks everyone for joining us today. Like and sub if you have not on YouTube. If you enjoyed this session and you're not yet in our community, we really think that you'll dig our community vibes in Discord. We'd love to have you jump in, throw your intro, and join us today. If you're not a Discord user, you may want to check out our weekly community calendar that you can kind of just scope out and see what you might be getting into, what kind of events are coming up this week and in the future weeks that you will be able to get very open and free access to. And finally, if you're ready to really accelerate the LLM application development for yourself or for your company, consider applying to cohort 1 of our inaugural AI engineering bootcamp, kicking off February 13th, Tuesday. This is going to be a full stack bootcamp, 7 weeks, where you'll learn to not just prototype complex LLM applications using prompt engineering, RAG, fine tuning, and many other advanced methods, but you'll also learn how to get those things deployed, operate them, improve them, and scale them in real production environments. Check out the syllabus for more info and consider if becoming AI Makerspace certified in AI engineering is something that aligns with your 2024 aims. Finally, please give us any feedback. We'd love to continue improving. We'll throw that link in the chat for those of you that want to offer something up. And as always, keep building, shipping, and sharing, and we'll do the same. We'll see you all next week.